In this question, arrange the following compounds in the increasing order of their dipole moment. So clearly we know that HBr, H2S, NF3, CHCl3 all are polar compounds which are having net dipole moment. But if I am going to take the compound NF3, NF3 is having 3 bond pairs and 1 lone pair. It is having pyramidal shape. Nitrogen is having sp3 hybridization. The bond pair, the lone pair bond moment is always in the upward direction. Nitrogen fluorine atoms, the fluorine is more electronegative. So the two bond moments are in opposite direction. That's why its dipole moment is very low. From the NCERT textbook, the dipole moment of NF3 can be taken as 0.24 debye. Debye is the unit of dipole moment. If I am going to take H2S, its dipole moment can be taken as 0.95 debye. And if I am going to take HBr, it is also a polar compound whose dipole moment is 0.79 debye. If I am going to take a chloroform, which is also having a dipole moment value 1.04 debye. If you are arranging in increasing order, then the dipole moment order is NF3 which is less than HBr less than H2S less than CHCl3, which is there on option 1, which is the correct answer for the given question. The maximum covalence of a non-metallic group 15 element E which belongs to the weakest E bond. So if I am going to take group 15 elements, nitrogen is there, phosphorus, arsenic, antimony, bismuth. These are the elements. Which element is having weakest E bond? You have to see here. If I am going to take N single bond N is having the lone pair. Here this N is also having lone pair. The nitrogen atom is small in size. That's why the lone pair repulsions are maximum in the case of N single bond N. Whereas in the case of P single bond P, size increases. That's why lone pair repulsions decreases. Bond strength is going to increase. So N single bond is the weakest bond in the group 15 elements. So what is the maximum covalency of the nitrogen means? If you write the electronic configuration of the nitrogen 1s2 2s2 2p3, only 4 orbitals are available for the bonding. That's why the maximum covalency of the nitrogen is 4 only. So option 4 is the correct answer for the given question. The species which does not undergo disproportionation reactions. So what are meant by disproportionation reactions means? The element that should undergo, the atom of an element that should undergo both oxidation as well as reduction, then that redox reactions are called as disproportionation reactions. If any element exhibits its minimum oxidation state or the maximum oxidation state, in those two oxidation states, then that particular element cannot exhibit the disproportionation reactions. So here chlorine, 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 chlorine. So if you see the chlorine minimum oxidation state is -1 and the maximum oxidation state is +7 because it belongs to the group 17. So chlorine cannot exhibit disproportionation reaction in -1 and +7 oxidation states. If you see the ClO2-, it is called as chloride ion. In chloride ion, chlorine oxidation state is +3. It can exhibit disproportionation reaction. If you see ClO4-, which is called as perchlorate ion, chlorine oxidation state is +7, which is considered the maximum oxidation state. In that maximum oxidation state, chlorine cannot exhibit disproportionation reaction. That's why perchlorate ion cannot exhibit disproportionation reaction. Option 2 is the correct answer. Hypochlorite ion +1 oxidation state, chloride ion +5 oxidation state. In these two oxidation states, chlorine can exhibit disproportionation reactions. See here the correct order of the following complexes in terms of crystal field stabilization energies. They are asking that crystal field stabilization energies. So in general we can tell that the complex which is having high splitting energy also having the stabilization energy, because we are calculating the stabilization energy in terms of the splitting energies. So all are cobaltic complexes. So if I am going to take CONH3 4 times 2 plus, it is a tetrahedral complex because coordination number is 4. CONH3 6 times 2 plus. It is an octahedral complex, but cobalt oxidation state is 2 plus. CONH3 6 times 3 plus. It is an octahedral complex, coordination number 6. Cobalt exhibits plus 3 oxidation state. COEN, ethylene diamine, it is a bidentate ligand, 3 plus, coordination number here also 6 plus, with the cobalt oxidation state plus 3. We know that COEN thrice. Here EN is a strong field ligand when compared to ammonia. If it is having strong field ligand whose splitting energy is more, whose stabilization energy is also more. So splitting energy is more for the complex which is having the highest oxidation state. Cobalt 3 plus is having higher oxidation state when compared to CO2 plus. That's why CONH3 6 times 3 plus is having high CFSE when compared to CONH3 6 times 2 plus. We know that delta T is equal to 4 by 9 into delta O. From that one we can tell that delta O is always greater than delta T. That's why tetrahedral complexes are having low CFSEs when compared to octahedral complexes. From this one we can tell option 2 is the correct answer for this question. So here statement 1, an element in the extreme left of the periodic table forms the acidic oxide. Extreme left of the periodic table having S block elements from group 1A and group 2A. So group 1A and 2A elements, most of them are metals which can form basic oxides. So the best examples are Na2O or K2O or CaO. All these are basic oxides, but acidic oxides formed given. So statement 1 is wrong. Statement 2, acid is formed during the reaction between a water and oxide of the reactive element present extreme right of the periodic table. So for example, if I am going to take Cl2O7, so it is nothing but acidic oxide of chlorine. If you are dissolving in water, you can get HClO4, perchloric acid. Acid is formed. So perchloric acid, acid is formed. So the statement 2 is correct. Statement 1 is false and statement 2 is true. That means non-metallic oxides are acidic, metallic oxides are basic. So identify the homoleptic complex that is a very low spin. So what is meant by homoleptic complex means the complex which is having only one type of ligands are said to be homoleptic complex. So FeCN5NO2 minus, it is not a homoleptic complex, it is a heteroleptic complex. Remaining B, C, D, E are heteroleptic complexes. From this one we can eliminate the option 2. So we should be low spin. So for example, if I am going to take COF63 minus cobalt 3 plus oxidation state, so 4s0 3d6 configuration, fluorine is a weak field ligand, that's why you have 4 unpaired electrons are there, it is not a low spin complex. FeCN6 4 minus, so the iron oxidation state is 2 plus, 4s0 3d6 configuration. Cyanide is a strong field ligand, so pairing of electrons against the Hund's rule takes place, 0 unpaired electron, so it is a low spin complex. C is the correct answer for this question. And the D, C1H3 6 times T plus, CO3 plus, again 4s0 3d6. Ammonia is acting as a strong field ligand in the combination of CO3 plus, that's why here also no unpaired electrons. Pairing of electrons takes place against the Hund's rule. So D is also a low spin complex. CrH2O 6 times Cr oxidation state is 2 plus, 4s0 3d5 configuration. It is an octahedral complex. So you are going to get the EG orbital at the top, T2Z orbital at the bottom. 5 electrons are there, 1, 2, 3, and H2 is a weak field ligand. So 5 unpaired electrons are there. Here it is a high spin complex. It is not a low spin complex. C and D are correct answers for this question. Option 3 is the correct answer. So niobium and ruthenium, X and Y of electrons in their respective 4d orbitals, find the value of X plus Y, they are asking. So we must know the niobium atomic number and niobium electronic configuration. So if you see the niobium atomic number, which is 41, niobium electronic configuration can be written as krypton 4d4 5s1 configuration, anomalous configuration having. So it is having 4d electrons. And ruthenium atomic number 44, its electronic configuration can be written as krypton 4d7 5s1 configuration. It is having 7 electrons. 7 plus 4, that will be equal to 11, is the correct answer for this question. The complex Ni2 plus and dimethyl dioxane contains dash number of hydrogen atoms. So in practical chemistry, nickel 2 plus can be identified by DMZ, dimethyl dioxane. Dimethyl dioxane structure can be written as CH3 single bond C double bond N single bond OH, single bond C single bond CH3 double bond N single bond O minus. It is a negatively charged bidentate ligand, and the nickel is going to form the complex called as NiDMG twice. That is the scarlet red color complex that is used for the identification of Ni2 plus. So if you see the nickel 2 plus oxygen, which is connected to N, which is connected to double bond C, which is connected to CH3. And this particular C is connected to C, connected to CH3, connected to N, which is connected to O, and O is acting as a donor atom, like this. And one more point, and here it is oxygen, which is connected to hydrogen, and which is connected to the nitrogen here. So OH nitrogen, which is connected to C through double bond, which is connected to C and which is having CH3, and here also CH3, double bond N, which is connected to O minus, which is going to donate the electrons towards the nickel. So the number of hydrogen atoms are 1 plus 3, 4, 4 plus 3, 7, 7 plus, here also 7 are there, 7 plus 7, that is equal to 14 hydrogen atoms are there.